Okay, so we talk about inductance is measured in henries. And I'm looking at my notes here where we're taking off from here, and I think it's a little redundant, so rather than, yeah.
Can you just go over inductance one more time?
I'm sorry, I moved on. Yes, I can. Yes, I can. All right, so as I was saying, my notes are a little redundant, which means repeating themselves. So inductance in a DC circuit, I'm not going to write this. So in a DC circuit, when does the current change in a DC circuit?
Beginning.
I can think of 2 times.
Off and on.
Off and on. Okay, so the only time you get in a DC circuit, the only time you get this problem is off and on. So in a DC circuit with only resistance, you don't see any of this, right? Because all you have is your wire and the wire's straight, so it's negligible. When the switch is closed, current begins to flow, but but in a DC circuit with inductance, which means I put a coil in a DC circuit. And where am I going to find a coil in a DC circuit?
Motor.
A motor. Where else?
Solenoid.
Solenoids, relays. All right. So in a DC circuit with an inductor, it's going to have inductance. So current no longer snaps up and snaps off instantaneously. So when that happens, when the switch is closed, current begins to flow, but is then opposed by EMF in the coil that you've created. So it actually takes a little bit of time for it to build up. You just don't notice it because it's, the time is very quick. The greater inductance, the longer it takes. And the same effect, when I shut down the circuit, it's going to oppose it. It's going to say, whoa, don't go anywhere. So you could possibly see something like this. Some examples where you can actually see inductance and counter EMF in play is if you have an incandescent or a light bulb, a regular light bulb, and you have a lot of inductance, it may see the light bulb take a second to come on. Kind of, whoa.
HIDs are that way.
Huh?
HIDs are that way.
HID
headlights.
I didn't notice. I don't stare at headlights. It explains a lot. Okay, so takes a minute for it to come up. And then when you shut down the power, you may see that light take just a second to go out. Like, man, didn't snap off. All right, so that because of a lot of inductance in a circuit, it could do that. So that would be building a circuit that has some resistors and coils and coils and coils and coils and a light bulb. Then you could see that. For those of you that have completed the project where you have a motor and the relays and such, one of the things I ask you to do, I say, tell me how much current is being drawn by the circuit. Everybody asked over that, right? Okay.
No, you skipped me to go to
Yeah, well. So, and then what did you notice with the amps?
shoots over and then
Peaks up and starts coming. Why is it coming back? Why is it this large draw and it's coming back? It's building up EMF. It's the same theory, but what it is inside the motor starts spinning. When the motor starts spinning, it creates its own EMF within the motor and changes the resistance of the motor. Because when the motor is not moving, those coils of wire are acting against other coils of wire, and it looks like a dead short because it doesn't see the coils acting upon the coils. But once it starts moving, it sees those coils, so to speak, and it builds up this counter EMF. See, that's where you see it, this peak in amps, and then it starts coming back. So that's another thing about motors in EMF, but it's the same concept. Is that helping?
Yeah.
Okay, good. All right, so I've kind of lost my timeline or my thing here, so now I guess I gotta go to stars and circles. It's not moving. All right, so where was I? Inductance. Let me see. Yeah, there was a 0.9 inductance into DC circuits, what I'm talking about, but I'm going to go with this right here, and I'll just put a little 9 right here, and I'd say that, now this is going to be a little confusing. I'll do my best. The amount of time, time constant. We'll just call this time constants. So how long does it take to happen? Why couldn't you ask me something like this, Prince? Well, how long does it take to build up? And I said, oh, stand by, I'll tell you. So the amount of time it takes for current to reach maximum is based on time constants. One time constant is the time it takes for current to increase or decrease, because it builds up and has to die down, to 63.2% of the previous value.
Where do you get 63 points?
It's a given. It's a known thing. So notice I haven't told you a time yet. I haven't said it's 1 second or a nanosecond or anything. It says a time constant. So how long that really is, I've yet to define. I've only said that it's going to take 5 of them. Did I say that yet? It's going to take 5 of them. And it's from, and of course you have to work with me, and I didn't create this. And of course you can't go 0 times, but that's the way it works. So I will write this to 5. So I'm going to keep doing this. So it takes 5 time constants to equal full value. And that's defined as greater than 99% or less than 1%. All right, so it's not 100%, it's not 1%, or 0, it's less than 1. So that equals full charge, full discharge. Follow me so far? Why 5? Why does it take 5 constants to go from nothing to something to full and from full back down? Well, if we worked at it backwards, and I said we're at 100% value, you might want to get your calculators for that. What is 1 time constant? What percent? Okay, if I have 100, sorry, not 100%, I should just say 100. My value is 100. Value is 100, and I subtract 63.2% of that. What do I get? And by the way, what is 63.2% of 100?
63.2.
Just happens to be 63.2. So what is left?
36.8.
36.8 is the value. So all right, I'm full charged, and I just lost 63.2% of my value of that charge, and I'm left with 36.8. So I'm left with 36.8, and I subtract 63.2%. What is 63%? I didn't write this down, the exact number, but if I subtract 63.2% from this number, I'm going to be left with? No.
Who gave this guy calculator?
Let me try this. Okay, playing along at home. 36.8 minus 63.2 second percent. I'm going to do this. This number in parentheses is how much we're actually subtracting. 23.25. I'm just going to round. Equals 13.54. Everybody follow me?
No,
Yeah.
Well, where did I lose you? It takes 5 time constants. Why 5 time constants? I have, let's say, a coil, and this is how long it takes the current to go from 0 to full or full to nothing. It's easier to show you full to nothing, all right? So I'm at 100%, right? Current's at 100%, and I shut it off. or we'll just go shut it off. Or I say, or it's going back the other way. So it's at 100%, and I shut it off. One time constant is how long it took to lose 63.2% of its level. That left me with 36.8. Here's 36.8. Subtract another 63.2%. What is 63.2% of 36.8? It's 23.25. Right there's what I minus, so I'm left with 1384. If I have 13.54 minus 63.2%, minus 63.2 second percent equals, that happens to be only 4 point, nope, so I'm left with 4.98.
Subtracting 8.55.
If I have 4.98 and I subtract 63.2%, I'm left with 1.83. If I subtract if I have 1.83 and I subtract 63.2% of that, I'm left with 0.67, which is less than 1.
Sorry, how are you getting the 23.25? And
It was given to me on gold tablets.
No, they
Huh?
23.2.
So 63.2% of 36.
This number here, 63.2%. Notice how it's the same?
Yep.
It's a given quantity.
But what I'm saying is that the one that you said 23.25.
Yep, I may have screwed up on that because I was not paying attention.
No, that was the.
That was
right.
63.2%.
36.8 times 63.2% equals, this is the number that I actually subtracted from here.
So that was the 63%.
That would equal 1355.
It's percent, people.
And then you
Oh, I see.
You get that?
Okay.
So 36.8 minus 63.
And I just didn't follow suit here.
Percent.
I think it's actually 4.98 again.
23.25, and then you subtract that from 36.8.
All right, follow that. That's why it's 5.
So the current is decreasing by this
By that much every time.
steps.
Yep, in these steps. So it takes 5 times.
and increasing the same steps, right?
Am I losing you guys? I got a whole bunch of conversations going on.
So what does this mean
You
then?
got
Is how fast the field builds and how fast it collapses?
Okay, if I ask you a question, how many time constants does it take for a coil to charge up or completely discharge? What's your answer?
5.
Thank you.
So you do it 5 times.
All right. How long is a time constant? In seconds.
Who gives a flying hoot?
No, that's not the answer. It
Depends.
depends. I haven't told you yet. But it takes 5 of them. Huh?
What?
Okay, how many time constants does it take to charge up a coil? How many time constants to discharge it?
5.
Okay, that's based on 63.2%. You're probably not going to need to remember that. You're not going to have to work this, but I just told you why, because somebody would have said, well, why 5 time constants? And I told you why. Don't make it a thing.
I actually wasn't wondering why.
I wasn't pointing at you. It's her now. She's my problem. All right. But I didn't tell you how long the time was. So a time constant is proportional to inductance and inversely proportional to resistance. More inductance equals longer time. Still takes 5 of them, but each one of them is longer. More resistance equals shorter time. The formula, which you don't need to remember, is time constant equals inductance divided by resistance. I have an example. Against my better judgment, I'll discuss it. If R is 10 ohms and inductance is 2 henries, how long is each time constant, and how long does it take for current flow to stop or completely flow? So it is time constant equals, I said I have 10 ohms and I had 2 henries. 2 henries divided by 10 ohms. So it takes 0.2 seconds. It's not that hard. So it takes 5, so a time constant is in 0.2 seconds. So in my scenario, it takes 5 time constants of 0.2 seconds to fully flow or fully stop, to make it easy. As the henries goes up, what happens?
Time gets longer.
Time gets longer. We can go back up here. I'm asking these questions right here. As the inductance goes up, it takes longer, and resistance goes up, it gets. So what? I'm gonna start using that. I know a guy who does. That's his always thing. So what? It's the point. So what is, with an inductor, voltage will be instantaneous. But it takes time for current to build up. Therefore, probably you just did this at the beginning and just moved on, right? Therefore, in an inductive circuit, the voltage leads the current period. But in a DC circuit, it only happens to start up and shut down. So, but in AC, that's what's happening. But in an AC circuit, because the voltage is constantly changing in direction and amplitude, this happens non-stop. I'm going to make some points here. Let's see. It's actually number 10 on my list. And it's what I just said. In an AC circuit, current changes constantly. Therefore, the effects of inductance happen constantly. So, because, well, hang on. So, my heading here is inductive AC circuit. And that is, in an AC circuit, current changes constantly. Therefore, the effects of inductance happen constantly. Okay, and I mentioned this. EMF, or CEMF, we'll say CEMF, happens with the greatest change in current. Where does my greatest change happen?
The first or the last.
All right, as I mentioned, there's not a lot of change between here and here. So if this is 0, what is this?
90. Oh, no. 180.
180, 360. So the greatest change is going to happen here. So from here to here is a huge change. So greatest change is going to happen. Greatest change is at 0, 180, 360, repeating. Then I'd actually be repeating 360, 180, 360, 180. I don't want to make this too complicated. I'll just tell you what it's on here, but I'm going to leave it at that. Counter EMF follows Lenz's law and opposes current change 90 degrees later. We also know that counter EMF is 180 degrees out of phase with applied voltage. Therefore, in a purely inductive circuit, and what kind of circuit is that? It's an AC, but what does it have in it?
Coils.
Just coils. How many resistors does it have? None. So it's just purely inductive. It's just an L. In a purely inductive circuit, current lags voltage, that's Eli, by 90 degrees. 90 degrees. And counter EMF is out of phase with applied voltage by 180, but I'm just not going to write that. So I just want to leave that. Purely inductive circuit, current lags voltage by 90 degrees. That's what we need to know. Yeah?
I'm still kind of confused on counter EMF. Like the difference between.
You may have to see me after. I kind of beat it to death a little bit. What?
It only leads by 90 degrees, so you can't just add more coils and get it higher, or get it further apart.
You'd never want to.
No, like if you wanted to get it to the next,
No, you don't.
You don't-
Then you've got to go all the way through the bad to get there.
you can't do that.
It's kind of like,
Like that's the maximum, the 90 degrees.
yeah. I was going to say it's kind of like
Then we'll cancel out that 180.
going somewhere, but I couldn't put that thought together. So, all right, computing. Computing inductance in a circuit. Good news. It is done exactly like computing resistors in a DC circuit. So in other words, inductors in series. L total, L for inductor, equals what? Help me out. L1 plus L2 plus L3, infinity. Inductors in parallel. Is L total equals 1 over L1 plus 1 over L2 plus 1 over L3, all of that, 1 over. Think you can do that? I mean, that wasn't hard, was it? This is assuming. This is assuming the inductors are placed far enough away from each other to not create mutual induction, which is where a coil is placed next to a coil next to a coil. Now they start interacting with each other, and that changes everything. All right, so we know how, if I gave you a circuit, of course now it's going to look like this. It's not going to look like a battery. And I did this and that, you're going to know how to add those up, right? Just like resistors. It's not very difficult. But that brings us to something called, well, we have this, but is that resistance?
No.
It's like resistance, but it's not. It's something different. It's called inductive reactance. So it's like, it is to resistance to resistors, inductive reactance is for a coil. So inductive reactance is the effect of inductance on a circuit. Inductive reactance is the effect of inductance on a circuit. And you are going to be able to figure this out. It is measured in ohms. Hey, sounds good so far. But due to phase shift, is not considered resistance. In an AC circuit, resistance is still going to be resistance that we get from resistors. What do we get from inductors? Read the board. Inductive reactance. Measured in ohms. So represented by X of L. An inductive reactance, I can now write X of L, I'm saving time now, is proportional to the inductance and the frequency. So in other words, if inductance or frequency, also called hertz, is increased, what happens to the inductive reactance? Okay, X of L goes up. The formula that you want to write on your formula sheet is X of L equals 2 pi F of L. So again, X of L equals inductive reactance. Uh, 2 pi, well, you know what 2 is, you know what pi is.
What does that say, FL?
FL. It's a little f. F equals frequency. which is in hertz, and L equals inductance. So, example. Or a question. What is X of L in an inductive circuit where the frequency is 60 hertz and inductance is 7, and what's it given in? Anybody remember?
Millihenries.
What?
Henries.
Henries. 7 Henries. So what is my inductive reactance? All right, so remember it's X of L equals 2 pi f L. So X of L equals 2 times pi. Pi is 3.14. We'll just do 3.14 times the frequency, which is 60, times the Henries, which is 7. Now, because it's all simple multiplication, we go from left to right. So 2 times pi, and on my calculator, I'm not going to do 3.14. I'm going to do 2 times the pi key, which is the third one down on this one, 2 pi, and that's going to carry it a lot further out because you're going to want you don't want to start rounding a bunch of numbers. You're going to get way off at the end because, oh yeah, this is the beginning. It's going to go very long. So 2 times pi, I'm just going to times 60 times 7 equals, what'd you get? 2638.9 what? Okay, X of L equals 2638.94 ohms. Everybody got that? Know how to get that? Are you certain? Okay, certainly. Questions? I have none. Yes.
You put due to phase shift is not considered resistance.
It's going to be, and I'm going to get to this in the end, but what we're going to do with any circuit, just like we did before, is we're going to figure out, we're given a voltage, we're going to figure out what our total resistance is and what our current flow is. But because of the way AC circuits work, you can't add inductive reactance, X of L, to the resistance to get R total. It's going to be a whole nother thing. So there'll be an R total, but it's not the R total you're used to. Because there'll be an R total, X of L total, and X of C total, and those are not going to equal R total.
It's like
It'll be Z. What?
It's probably going to be like the challenge, right?
It's going to be just like it. The only thing that the feedback that I have received is that the formulas that I use and the technique that I use doesn't seem to match that. But the feedback is that they like the way I do it better. It's a little more simplistic.
Really? 'Cause right now I'm feeling like that is way more.
What is more simplistic?
The
Challenge.
challenge.
As long as you get the right answer, I don't care how you do it. Well, I do care. If you use an online calculator or something along that nature, I care. You got to be able to do it with your calculator in your brain. So, all right. So that, what's the formula for finding inductive reactance?
Over there?
Yeah.
Oh, hell, I don't
It's
know.
exactly the same.
I know. There's only like one nuance difference.
Yeah.
So, all right. So that's how you're going to do inductive reactance. That's all I got to say about that. Now we're going to talk about capacitors. But before we do capacitors, all right, capacitors.
Like round or whatever, but then air thing doesn't do it.
Well, here's the good news about capacitors. Good news and bad news. If you understand inductors, it's very simple to understand a capacitor. If you're completely lost with inductors, you're going to get more lost. So make sure that if you don't understand something, you're asking for some help. So capacitor. One thing that was Ivan brought up is a capacitor is also known as a condenser, depending on its usage. So you can look for that. But capacitor. So a capacitor is a device that stores electrons. What does that sound like?
Battery.
Like a battery. Of course, I wrote here like an electrical accumulator, but then I'd have to explain an accumulator to you, which probably wasn't the best word, but like an electrical accumulator. Which is, okay, so we can say it's like a battery. It's a very short-lived battery that doesn't have much in the way of amp hours at all. But it's like an electrical accumulator, and I say that, but now I have to explain what an accumulator is. In hydraulic systems, there's things called accumulators. And what you do is you have a hydraulic line, and you may have this container that's symmetrical, and there's a bladder inside and a charge of air. There's a lot of air in here, PSI. And so it can move this bladder, goes up and down. But what happens, because fluid is red, fluid comes in and it fills this up and pushes this down. And it's under a charge. And so perhaps maybe the hydraulic pump can't keep up. Well, then the pressure under here pushes the fluid out and helps the pump for a second. And then when the pump stops, this will fill back up. And it also takes hammering out of the system and stuff. So it just takes a small charge of electrons, just like a very tiny battery that is, like I said, very, very low on the amp hour scale, but can store a lot of voltage. And if you want, I can show you how to charge them up and leave them setting around. So when somebody picks them up, they get the snot knocked out of
Is that
them.
what they use in like cameras for flashes?
Yeah, charges that. So there's a lot of uses. We're going to talk about more and more uses of those. I still have time. If I had a battery, I've got a nice capacitor. I can show you how it worked in my office, but I forgot to bring in a battery. We'll do it tomorrow. Consists of two conductors, more appropriate called plates, that can hold an electrical charge and are separated by an insulator, also called a dielectric. Dielectric. So I have a plate and some sort of dielectric, an insulator material, and another plate, and it just so happens that that is the schematic for it, without the little red squiggly in the middle. So isn't it funny? And I keep telling you, draw things. Don't use the new convention where it's like, like that and say, oh, capacitor. Don't do that. Or what's the other?
Oh.
Relay.
Yeah, relay.
Draw it by the old convention. You can see what it is, and there's a representation. Here it is. It's these two plates. And the plates are very close together, and there are periods of time, especially in AC, when it doesn't notice that they're not connected. Now in DC, I have a DC circuit. What is this called? It's called an open. It doesn't flow. So if I built a DC circuit that looked like this, what am I going to get? Nothing. Well, in theory, what will happen is this will charge up very quickly and then it's just dead. So if I have a light right here, I'll show you this tomorrow, and I turn it on, the light will start to go and then it's just dead. And when I open the circuit, it'll start to go and then it's dead. So it'll only work for a very brief second while this charges up. But take this out, and put this in, what's that symbol mean?
AC.
AC. AC, what happens is the electrons start flowing one way and they start filling up this plate. By the time the electrons realize that there's nowhere to go, well, this has already changed direction. It's going that way. So it's like, hey, everybody go this way. No, never mind, we'll go this way. And then it starts filling up this plate. And by the time this plate fills up, it changed around again. So it's constantly moving back and forth. And so in an AC circuit, you can put a capacitor in series and it actually works because of the constant reversal. And I'm personifying the electrons, but it kind of tricks them into working. Let's see. The ability. The ability of a capacitor to store electricity is known as capacitance. Capacitance. And is measured in farads. F. Hey, remember Michael Faraday from when I first started talking? I said there's Henry, and then I said, what did I say? He was partners with Michael Faraday, who gives us the farads. Funny thing is, 1 farad, 1 F, is a very large number. One farad, 1 F, can store 1 coulomb. What was coulomb? 6.28 times 10 to the 18th. Yeah, I was right, 18th of electrons. At 1 volt. I think I took it out of my notes because I thought it was so ridiculous that it couldn't be right. And I couldn't find, but then I found out it was right, and I never put it back in. But it's something like the amount of surface area actually needed to create 1 farad was measured in, do you know? It's like in acres or something. It's some ridiculous number. It's giant. A true 1 farad capacitor, let me show you this right here. All right, this blue thing right here is a capacitor. This is another capacitor. Let's go. You can guess the right capacitance on this. I'll let you go early. Throw out a number.
10 microfarad.
10 micro.
7.
That's 0.025 of a farad.
Wow.
I think it's huge. So we'll play with this tomorrow.
So like Hoover Dam, do they produce like farad?
That doesn't. You don't measure that in farads. Farads are capacitance.
You know when they're storing though.
They don't store it. All right.